I'm here to talk about cache mapping techniques and replacement algorithms in the cache memory. And we all know the meaning of the cache memory, which is just the memory between the processor and the main memory that is used to access data which is frequently used by the user. And we shall be defining different aspects of the mapping techniques and the replacement algorithms. Let's get started. My name is Kabagere Salim and I'm a student of Makerere University in year one. Okay. The cache mapping techniques are these are just the methods used to determine how data can be stored and retrieved from the cache memory. And as we shall be seeing, we have three types of the mapping techniques, and they range from direct associative and set associative. And in many contexts or many books, we shall find the associative method being referred to as the fully associative method. And let's get started and see what each type represents. Okay, beginning with the direct mapping, and I'll begin by defining it. In a direct map cache, each block of main memory maps only one specific cache line, and the mapping is typically determined using a module operation on the memory address. For example, if the 32 cache lines, a memory block might map cache line 0 if its address module 32 equal to 0. And we shall see what this one represents. Let me first show you what it literally means. As we are seeing here, if assume the cache size is 16, so it means we shall be having from 0 to 15 words, and assume its number of lines that are 4, so we shall be beginning from 0 to 3. So if the cache line is 0, it will be mapped to the memory block of 0. Assume this is a memory size of 64. We shall be having from 0 to 63, that's from 0 to n minus 1. And assume the number of blocks, of course, the number of blocks will be getting the cache, the memory size, which is 64, and we divide by the block size, which is 4, getting 16 blocks. So that's why we are having from 0 up to 15. So any cache line which is 0, it will be mapped to the 0 block, just like you see. And then that of 1 will be mapped to the 1 block, that of 2 to the 2 block, that of 3 to the 3 block, that of 4 to the 4th block. And after being 4, it means we shall not get done with memory. What we shall do, we shall again begin. The fourth one shall be mapped to the 0 block of the main memory, just like you see. Yeah, from here from here to also be mapped to 0 0, here to be up to 0 1 2 3 4, just like that. It's directly mapped to the, if the cache line is 0, to also be mapped to the memory block, which is 0, just like that. If it's 1, be mapped to the memory block of 1 2, just like that, direct as it sounds. Then now we got the set associative mapping. We are saying set associative mapping is a compromise between the direct mapping and associative mapping, and we shall see the associative mapping in the later topic. But let's begin with the set associative mapping. In this technique, each cache set contains multiple cache lines. It will depend on the sets you want to do. If you want to do 2 sets, 4 sets, 8 sets, doesn't mind, as long as you have enough hardware to contain that. So we are saying memory blocks are mapped as a specific set within the cache using a similar module operation. The block can be placed in any of the cache lines within that set. Yeah, we shall see how the set associative mapping works. The saying cache associative mapping reduces the likelihood of cache conflicts compared to the direct mapping. Yeah, we can see in direct mapping, we are having a lot of cache misses compared to the cache hits. The cache misses are very many in the direct mapping. So literally the set associative mapping comes in and solves this problem, as the reduced cache conflicts, there are less cache misses compared to the cache hits. More of them than the cache hits, and the cache misses are very few because of the setting. I mean, because of the grouping that we do in this. Yeah, let's go continue and I show you how the set associative mapping is done. Yeah, the set associative mapping. You see, uh, we group different blocks into sets, and we first determine which which um, which block is going to be mapped to which cache line. We do that by getting we get the block number, we divide it by the number of sets you want to do, and the remainder is just the number. It will just be telling you that the cache line in which you have to store that data. So after storing that data in your cache lines and all that, you know the sets and the contents in each set. So you can literally retrieve each data depending on the sets there are. Yeah, just like you see here, we have this set, we have this set, we have this set, we have this set. In this context, we have the four sets, and we can easily retrieve that data depending on the four sets we have. And this reduces the cache misses because the data is specifically organized in different sets, and this retrieval is quicker compared to the direct mapping. Yeah, let's go to the associative mapping, and we are saying in an associative cache, any block of memory can be placed in any cache line. There are no specific constraints on the mapping. Yeah, for the associative mapping, everything there is random. It's done at a random pace. It's not something like you have to know this block maps to this cache line or what. As long as there is space, everything is mapped to any. I mean, any block is mapped to any cache line, and any cache line is mapped to any block. As long as there is space, it doesn't require to know that it's going to be mapped onto this. That's why they're saying there are no specific constraints. Everything is random. You do that in a random manner. There is nothing like you have to know this and that. Yeah, so I'm saying this offers maximum flexibility but also requires complex hardware to search for the data in any cache line, making it slower and more expensive than any other mapping techniques. Yeah, just like when you're in a big room and something is in a big room and you're told look for that thing in that room, it literally becomes very hard for you to retrieve the object in that room because you have to search around in many places, like in many areas around that room to retrieve that thing. That means it becomes very hard for you to easily get it, and compared to a small room, in a small room you can easily know it's here, it's there. So literally, that's why we are saying it requires complex hardware to search for that data in any case line, because you know it's something very huge. I mean, in associative mapping, it's random. That is stored in any place, in any car, in any block. So it becomes very hard for the processor to retrieve that information from the cache because it's literally very hard for it to, to determine which block it is and all that stuff. So it just requires complex hardware and it's slower. I mean, taking too much time looking for this and that. It's more expensive. Yeah, assertive mapping, effectively eliminates cache conflicts, but it's rare used in practice due to the complexity and cost. Yeah, it becomes very expensive. Let me show you something about it. Yeah, just like you see, uh, any block can be mapped to any cache line. Yeah, this one can map to this, and this one can be mapped to this. This one can map to this, depending on where space lies and where space is. So it doesn't need you to know that it should be mapped on this block or what and what. No. Any place, anywhere, you just place your data in that block. Yeah, doesn't need any specific constraints for that. So that's what I can tell you about the mapping techniques. Let's go to the replacement algorithm. Yeah, just replacement algorithms determine which cache block is selected for eviction in case a new block is to be loaded and the cache is already full. So this one just shows you which cache block is to be selected. Remember, it just applies in case the cache is already full, and it shows which cache block is to be selected for eviction. to be selected for eviction in case the cache is already full, the cache memory is already full. So it doesn't do it in a disorganized way. No, it has to follow some commands, some principles of the cache memory. And these are the replacement algorithms that we do have. We have the least recently used, which is the LRU. This just it's one of the most well-known replacement algorithms. It evicts the cache block that has not been accessed for the longest period. Yeah, just like it sounds, the least recently used. So it will see the least recently used cache block, and it will be the one which is, you know, which is evicted, and the new block will be put in that place for that cache block which was not yet always used, which was least recently used, and yeah, the new block will be placed in that one will be evicted. Then the second one, we have the FIFO, which is the first in first out. It means the first block which was retrieved first, it will be the one to be evicted first to create room for the new block that is coming in. So that's it. Just says the FIFA replacement algorithm removes the cache block that has been in the cache the longest. It treats the cache as a circular queue, and the block that was brought in first is the one that gets replaced. So the second one is random replacement, just like a random sounds. Just it does this in a random way, in a random manner. It just picks out anything at random and selected, and it's evicted, and that thing is the new block is replaced. It's put there. So it says in this approach, a random cache block is selected for replacement. While this algorithm is simple to implement, it does not make intelligent decisions. Just like you do something randomly, it doesn't need a lot of decisions or a lot of thinking. So that's why I say it doesn't make intelligent decisions based on access patterns. These are the access patterns that we do have, and saying the random replacement doesn't follow these access patterns. Just do it. It just does its thing in a weird way. It doesn't follow intelligent decisions. So that's why it's not effective and efficient, because it makes a lot of errors, and yeah, depending on the luck, you might do the hits, but this one brings a lot of cache misses. Then the least frequently used, that this one just replaces that cache block that is least used. It maintains a counter for each cache block, and the block with the lowest access count is evicted. Just like I said. Then you have the most recently used. It's the most recently used replaces the cache block that has been accessed most recently. Unlike the least recently used, the most recently used takes into account the most recent accessed block and the oldest. So it just replaces the block that is most recently accessed, or that is mostly recently used, and it's replaced instead of the other ones. It's the one that is replaced to create room for the new block that's coming in. Then last we have the adaptive replacement cache, which is the ARC. The ARC is a self-tuning replacement algorithm that dynamically adapts to changing access patterns. It combines elements of it combines all the prior things I've said already. So that's the adaptive replacement cache access. Okay, replacement algorithm or access pattern. Yeah, I think we're done for today. Thank you for your time. Yeah, I remain Kabogaye Salim, a student of Makerere University. Thank you.